Welcome to the lesson on lean building blocks. Upon completion of this lesson, learners will be able to discuss some of the building blocks of lean manufacturing such as pull system, Kanban, cellular manufacturing, total productive maintenance, total quality management, point-of-use storage, quick changeovers, and batch reduction. Learners will also be able to examine some of the tools and techniques used to implement lean manufacturing principles. Lean uses several principles to reduce and eliminate the 7 sources of waste related to transportation, inventory, motion, waiting, overproduction, overprocessing, and defects. Although these building blocks can be implemented individually, the overall improvement is much greater when they are used together. For a lean initiative to be successful, the entire company from the top down must be considered in the changes. Lean is a continuous improvement process, so new ways to improve should constantly be considered. The basic lean building blocks discussed in this lesson include pull systems, Kanban, work cells, total productive maintenance, point-of-use storage, total quality management, quick changeovers, and batch reduction. The pull system, also called pull production, is an integral element of a lean manufacturing system. But before this, we need to know what a push system is. A push system is the traditional method of production, where parts are produced based on a forecasted or expected schedule, without regard for the current downstream consumers. The typical push system essentially pushes large quantities of products through the manufacturing process as quickly as possible based on anticipated but not actual demand. Downstream refers to future processes or stages in the supply chain. Upstream, the opposite of downstream, is a term used to describe previous processing steps. An example of upstream processing might include all the suppliers of raw materials. Upstream and downstream processes are very important in lean manufacturing because a glitch anywhere in the supply chain can delay delivery to the customer. A pull system, the opposite of a push system, is a more dynamic and responsive production system, where parts are produced in small batches based on immediate downstream demand. When a downstream demand is recognized, parts are pulled through production. Just-in-time, abbreviated as JIT production, coined by Toyota, is a pull production system that makes the right part at just the right time. JIT is also a way of thinking. The just-in-time mentality in lean replaces the just-in-case mentality that many companies have. What are the benefits of a pull production system? First, pull systems reduce the unit cost of each item produced. Low inventory costs, a reduced space requirement, and a reduction in rework and defect costs all result in a low unit cost. Low unit costs mean that the company is able to supply a reasonably priced product to the customer while still making profit. Pull systems also provide great customer service. Shorter cycle times for orders means shorter lead times and less waiting for the customer. This means customers receive their product quickly and to their specifications. Furthermore, pull systems produce a more predictable and high-quality product than push production systems. The second lean building block is Kanban. Kanban, the Japanese word meaning signboard, is a production scheduling system that uses signals to indicate demand for a product, which is driven directly by the customer. A Kanban system supports pull production and just-in-time because a signal to begin production is sent only when there is a customer demand. A Kanban card is the device used to signal the demand for any given product. They give information on the product type needed, the deadline, and the quantity required. Kanban cards can be physical slips of paper, emails, or automated electronic signals. Let us look at the 6 rules for an effective Kanban system identified by the Japanese company Toyota. A Kanban card signals the start of work, and no tasks can be initiated without this authorization. Each Kanban card specifies the quantity and type of items to be produced, effectively controlling work in process throughout the system. The number of Kanban cards in circulation directly influences lead times, while quality control is maintained by preventing defective items from moving to subsequent processing steps. Finally, the system maintains order fairness by processing requests in the sequence they arrive, following a first-come, first-served principle. Let's look at how a Kanban system could theoretically be applied at an EV manufacturing facility. A technician assembles an EV battery and uses the last 2 battery modules from the supply shelf. The technician scans the empty bin, triggering an electronic notification to the warehouse to replenish the battery modules, which act as a Kanban card. Warehouse staff retrieve 2 battery modules from inventory, scan their barcodes for stock tracking, and deliver them to the production line. When the barcodes are scanned, an automatic notification is sent to the battery module supplier, creating another Kanban card. The supplier receives the notification and ships the required battery modules to the EV manufacturing unit to maintain stock levels. The third building block discussed in this lesson is the work cells. The layout of a traditional manufacturing facility is based on the function of each process. All the cutting processes are grouped into one area, all the packaging processes in another, and so on. In traditional manufacturing, a large group of materials are sent through one process and are then delivered to their next process, where they wait in their original large batch. Lean uses an approach to facility layout called a cellular system. Cellular manufacturing or cellular system is a facility layout method that is based on the sequential flow of the product. A cellular layout supports the continuous flow of an individual product family, which reduces weight and transportation. A product family is a group of parts or products that have similar characteristics, which allow them to be processed in a similar way and sequence. Cellular manufacturing is sometimes called a one-piece flow system. A cellular layout supports the continuous flow of an individual product family, which reduces weight and transportation. A work cell or product cell is an area designated to a specific product family. Work cells provide operators with all the resources, equipment, and tools necessary to complete processing on one product family. The best layout for the work cell depends on the process. The most common work cells, like the one shown, arranges anywhere from 15 machines in a U-shape, making material entry and exit points near one another. Using a work cell layout requires employees to have a wider range of experience so that they can operate all machines within their assigned cell. Cellular manufacturing offers several key advantages in production systems. Material flow improves significantly as parts move continuously through processing steps until completion, virtually eliminating work-in-process inventory and reducing lead times. Transportation needs decrease since all processing occurs within the cell rather than across different departments, minimizing both part movement and operator travel distance. This manufacturing approach promotes shorter setup times, which further contributes to reduced lead times. Since speed is critical to a successful pull system, any holdup in production is a problem. Machine breakdowns and equipment failure can cause major delays in production, which can potentially lead to customer dissatisfaction. Total productive maintenance, abbreviated as TPM, is a preventive method for reducing equipment breakdowns through maintenance. A focus on increasing machine uptime and engaging every level of the organization are key. Machine uptime is the amount of time that a machine is properly running. TPM involves anyone who comes in contact with the machine, including machine technicians, maintenance workers, and even vendors in high-level management. It emphasizes the importance of preventative maintenance and advanced corrective maintenance. The goal of TPM is 0 breakdowns and 0 defects. To successfully implement a TPM system, the following factors must be considered. Scheduled maintenance. Plan routine maintenance checks while machines are operational to prevent breakdowns. Quality maintenance. Address root causes when detecting abnormalities or errors. Operator maintenance. Empower operators to perform basic maintenance, inspections, and document issues on their machines. Proper training. Ensure all staff, from operators to management, receive adequate training for equipment operation and maintenance. Advanced corrective maintenance. Focus on improving machines beyond repairs to prevent recurring failures. Safety. Prioritize employee and consumer safety throughout all processes. Total productive maintenance delivers multiple advantages to manufacturing operations. Machine performance reaches optimal levels while unscheduled downtime and breakdowns decrease significantly. Production output and flow increase along with better utilization of both production time and labor resources. Product quality is improved notably as equipment operates at peak efficiency. The systematic maintenance approach also extends equipment lifespan substantially. Next, we will discuss 2 tools that can be used to implement a TPM system. The first is Overall Equipment Effectiveness, abbreviated as OEE. This tool measures the effectiveness of equipment and is a means of identifying and controlling the 6 big losses associated with the equipment inefficiency. The 6 big losses, which are the main contributors to lost efficiency, include breakdowns, setup and adjustment delays, idling and minor stops, slow running speeds, quality defects and rework, and reduced startup yield. OEE categorizes these efficiency losses into three categories: availability, performance, and quality. This helps identify the factors that have the largest impact on lost productivity. First, calculate the efficiency of availability, performance, and quality using the equations. Then, to get the OE, multiply them all together. The goal is to increase the OE and remove the losses. The availability loss is associated with breakdowns and setup adjustment contributors. Performance loss is associated with idling, minor stops, and slow running speeds, and quality loss is associated with defects, rework, and startup yield contributors. Let us explain OE with an example of an EV paint shop's robotic sprayer. The sprayer achieves an OE of 72% due to daily nozzle cleaning downtime, categorized as availability, occasional paint flow slowdowns, categorized as performance, and rare quality defects requiring repainting, characterized as quality rate. By multiplying these three factors, 90% availability times 85% performance times 94% quality, the team identified that the biggest opportunity for improvement was reducing the paint flow slowdowns that were causing performance losses. The second tool used to implement TPM is Poka-Yoke. This is a fail-safe method or device used to prevent and detect defects. It takes two forms: preventive Poka-Yoke and detective Poka-Yoke. Preventive Poka-Yoke does not allow defects to occur in the first place. An example of preventive Poka-Yoke is a SIM card's shape that only allows it to be inserted into a phone the correct way. Detective Poka-Yoke sends a signal when an error is made. An example of detective Poka-Yoke is the sound a car makes when the lights are left on. The fifth building block is Total Quality Management, abbreviated as TQM. This is a continuous improvement system that focuses on improving all processes involved within the company. TQM is a management model that considers everyone's role in the company, the consumers, and the suppliers. This includes all employees, management, customers, and everyone in between. TQM relies heavily on employee involvement and customer involvement to improve the products and processes long term. The fundamentals of TQM create a shift from the importance of economic gain to the importance of quality improvement. TQM is a term that may come up during a lean project, but is more commonly used by management. New procedures on the production floor and environment or culture changes may be the result of TQM initiatives. Point-of-use storage, abbreviated as POUS, is the sixth lean building block. Traditional manufacturing facilities usually have one large centralized storage area. All products are received from a vendor at a common dock, unloaded, staged, and transported to their appropriate location or bin within the storage area. Then, when needed, the materials are picked and transported to the part of the facility where they will be processed. The large storage area may be located far away from the different processing areas, which leads to excessive transportation and motion. Lean principles suggest a different method called point-of-use storage. Point-of-use storage is a way to reduce motion and transportation wastes by sending materials directly to their next step in the process instead of to a large centralized storage area. Point-of-use storage can be used on a facility-wide level and on a smaller process-to-process level. On a facility level, each facility should have several point-of-use receiving docks located in close proximity to their corresponding department or processing area. Received materials can go directly from the receiving dock to the area of the facility or department. On a smaller scale, point-of-use storage can be used between processing steps. After a part is processed, it goes directly to its next processing location instead of being stored at another location. Following World War II, small automotive companies like Toyota could not afford to keep up with the mass production trend. Companies like Ford used highly specialized equipment that could produce identical car parts by the thousands. Toyota, unable to buy large specialized machinery, began producing small batches of multifunctional machines. The use of small batch sizes on general-purpose machines created a need for quick changeover times because changeovers occur more frequently. A changeover is the reconfiguration of machines and processes so that the appropriate part can be produced. Changeover is the breakdown and setup of machinery so that it can accommodate the next product to be produced. If general-purpose machinery is used to create multiple different parts, changeover time is an important factor in controlling process bottlenecks. The importance of changeover time is apparent in EV battery manufacturing industry, where rapid changeover of battery pack assembly lines between different vehicle models enables manufacturers to flexibly respond to varying market demands while maximizing equipment utilization and production throughput. SMED, or single-minute exchange of dies, is a method used to reduce changeover times so that each setup or changeover is reduced to a single-digit TURI time. Single digit or single minute means less than 10 minutes, but the goal of SMED is to make the time as small as possible. SMED implementation makes smaller batch sizes practical, increases product flexibility, reduces manufacturing time, improves response time to demand, and standardizes the changeover routine. The result of SMED is a changeover process that is standardized, repeatable, and one that workers can easily adjust to. Let us now discuss the final building block, batch size reduction. Traditional manufacturing is focused on producing in large batches, hence the term mass production. Systems like this perform a single operation on a large quantity of parts before they are moved to the next processing step. A batch size is the amount of product or material that is moved to the next processing step at a time. Lean manufacturing suggests that reducing the batch size can improve the efficiency of the whole system. One-piece flow occurs when the batch size is reduced to just one part, allowing each item to move through the process individually. Batch reduction offers several benefits, including improved product variety, reduced production time, and better quality control. We will discuss these benefits with relevant examples in the upcoming slides. While large batch production requires processing 100 identical battery packs before switching configurations and involves additional sorting and rework for custom orders, small batch manufacturing offers superior flexibility. By assembling each battery pack to order, manufacturers can switch between standard and extended range configurations as needed. This approach eliminates the inefficiencies of large batch processing and allows for better customization without the burden of sorting and rework, ultimately improving production responsiveness and customer satisfaction. In evaluating time efficiency between batch sizes, the contrast becomes clear in frame assembly operations. The large batch approach involves welding 50 frame assemblies consecutively before moving the entire batch through painting and component installation, which creates substantial work-in-process stacks between stations. In contrast, small batch processing completes the entire weld paint component cycle for one frame before beginning the next, effectively eliminating sorting and storage time. This approach reduces production delays and minimizes the inefficiencies associated with managing large WIP inventories between workstations. Finally, the impact of batch size on quality control is evident in motor manufacturing operations. In large batch production, testing 200 motors after assembly can lead to significant complications when defects are discovered, such as a bearing defect that requires inspecting all units to identify affected ones. Small batch processing offers better quality control by testing each motor immediately after assembly, allowing immediate detection of issues like bearing problems on the first unit. This enables quick process adjustments before additional defective units are produced, significantly reducing waste and rework while improving overall quality outcomes. In summary, a number of different tools, including overall equipment effectiveness, Poka-yoke, and SMED, are used to implement the building blocks of Lean. The building blocks of Lean include the pull system, the Kanban scheduling system, work cells, total productive maintenance, total quality management, point-of-use storage, quick changeovers, and small batch sizes.